Good morning. Last time we looked at a couple of problems introducing the concept of the displacement method for solution of a beam with settlement, and then we solved a frame problem where we saw that the displacement was also an unknown, and therefore, we had to write an additional equation to be able to solve for the displacement also. Today, I am going to take the same problems and I am going to introduce another concept to you. Remember, we wrote the slope deflection equations as 4 EI upon L theta A B plus 2 EI upon L theta B A minus 6 EI upon L squared delta B A plus fixed end moment at A B, that is the moment at A B. Now, today I am going to introduce you the concept where I am going to eliminate the delta. In other words, I am going to redefine my theta A B and theta B A so that you do not need to consider delta at all in the equation. So that if you look at the slope deflection equations, they will look this way: M A B is equal to 4 E I upon L theta B A plus 2 E I. In other words, I am eliminating, only thing is that these have to be defined differently. Of course, similarly, MBA is going to be equal to 2 EI upon L theta AB plus 4 EI upon L theta BA plus fixed end moment at BA. Okay. The only thing is that theta AB and theta BA are not the same as those defined in the earlier equations. Okay. So, let us look how we defined theta AB in the earlier equations. In the earlier equations, here theta AB and theta BA rotation from the undisplaced position to the tangent to the elastic curve. Okay. So, theta AB and theta BA as defined in the earlier equation were rotation from the undisplaced position to the tangent to the elastic curve. Okay. So, from original to the tangent. That is how rotation is defined, and I took counterclockwise as positive. So, that is this. Now, let us look at what happens when we have just a displacement. When we have a displacement, what is theta? From the original to the tangent, from the original to the tangent. So, in this case, when you have delta B A, what is theta A B and theta B A? Both equal to 0, because the tangent to the elastic curve at both positions from the original displaced position. So, this is the original displaced theta, this is the original, this is the original tangent, final tangent, original tangent, final tangent, original tangent, final tangent, original tangent, final tangent. So, they are equal to 0. This is the previous definition that we had. Today, I am going to introduce you to a new definition. I am going to say, let us look at that same. The only thing now I say is that this is defined differently. This is the chord that goes from A to B. Okay? From the chord that joins A to B to the tangent is my theta A B. Theta B A. Okay? So, what are theta A B? Okay, in this particular case, you will say, well, how is it different from the original? But the whole definition is different. Rotation from chord joining A to B to the tangent to elastic curve. So, therefore, it is now rotation from the chord, it is not rotation from the tangent in the undisplaced position to the tangent of the displaced position. It is rotation from chord joining A to B to the tangent to the elastic curve. When there is no displacement of B with respect to A, they are the same as what I had originally defined. But let us now look at this case, where I get delta B A. In this case, only delta B A, right? So, now the chord joining A, now B has moved here, okay? Chord joining A to B is this line, okay? Chord joining from A to B to the tangent of the elastic curve. So, in this particular case, since this is L, what is theta A B equal to? From the chord to the tangent, theta A B is equal to minus delta B. What is from the chord to the tangent? Since these are clockwise, okay. So, this is my definition of the new definition of theta A B, from the chord joining A to B to the tangent. So, now you see that this becomes my theta A B, theta B A definition. Now, the proof of this is to show that both of these give me the same moments. In this particular case, what is MAB equal to? MAB is equal to 4 EI upon L theta AB plus 2 EI by L theta BA, and MBA is equal to 2 EI by L theta AB plus 4 EI by L theta BA. Here, what would MAB equal to? MAB would equal to minus 6 EI upon L squared delta BA, and MBA would be equal to minus 6 EI upon L squared delta BA. These would be the moments at the end. Okay. So, let us see whether we get the same MAB and MBA. Here, well, there is no difference. So, MAB would be equal to 4 EI upon L theta AB plus 2 EI by L theta BA, and MBA would be equal 2 EI by L theta BA plus 4 EI by L theta AB and this theta BA. Now, let us look at this. See, here there is no difference because theta AB and theta BA are also the same. Let us now look at this one. Here you see MAB was equal to this thing. So, now MAB is going to be equal to 4 EI by L theta AB plus 2 EI by L theta BA. Now, let me plug this in. 4 EI by L theta AB is minus delta BA by L plus 2 EI by L theta BA, which is also minus delta. Substituting this, you will get minus 6 EI L squared delta BA, and you will get similar MBA also. The point to note is that we have got exactly the same MAB and MBA as we had got using the earlier definition. So, therefore, there is no difference in the entire method. The only point here is that we have negated the effect of trying to take delta BA in the equation. What we have said is, so therefore, we have simplified our slope deflection equation to just containing 3 terms, one containing theta AB, one containing theta BA, and one containing delta fixed end moment. Okay. So, essentially you may ask, what is the reason behind this? We will slowly come to what the reason behind this is, okay. But the point that I am trying to make is that this definition of theta AB and theta BA from the chord to the tangent of the elastic curve is completely equivalent to the previous definition. The only thing is that in the previous definition you had theta AB, theta BA, delta BA, all these as terms, and here you only have theta AB and theta BA. Okay. The advantage of this will become obvious a little bit later on, but let us now see whether if we can use this concept to solve the problem that we had solved last time, which was, remember. So, we will look at the problems and see if we get the same answers. Okay. That, I think that is the key thing. Okay. Here we are given, remember this problem, okay, and here you were given that this is A, this is B, this is C, and this goes down by 0.03 meters. Okay. You were given that E is equal to 200 GPa, I is equal to 2 into 10 to the power of minus 3 meter fourth. Okay. So, this is what you were given, and essentially what you were asked to find out is the bending moment diagram due to the settlement alone. Okay. Only B settles by 0.03 meters. Okay. So, let us try to solve this problem using the new approach that we have. Okay. So, if I were to take just this displacement, what would it look like? This is fixed. This is displacement. This is displacement. Okay. Okay. That is due to 0.03. Then let us see what happens when I have theta BA. See, we know that the degrees of freedom are this and this. So let me put it equal, so that once I have this, and then I have, this is theta B equal to 1. This is with delta equal to 0.03. This is theta BA equal to 1, and then finally we have this is theta C equal to 1. So this is delta, this is theta BA, and we can find out all the things that come out of it. So let's see. Due to all of this, what is theta BA? Now note that theta BA is, theta AB is now defined from the chord to the tangent. From the chord, so here the chord would be this, A with B, and this would be this way, the chord. Here the chord is this, here the chord is this. So let us look at what theta AB is. Theta AB here is equal to 0. So theta AB in terms of theta B is 0. Theta AB in terms of theta C is 0. Okay, and in terms of delta, it's going to be equal to, let's see, from the chord to the tangent, it's positive. So theta AB in this case is equal to 0.03 by L, which L is 10. This is, remember, this was 10 and this was 10. Okay. So theta AB is 0.03 by 10. What about theta BA here? You will see that theta BA is also .03 by 10. Let us see what theta BC is from the chord to the tangent, from the chord to the tangent, from the chord to the tangent, clockwise. So theta BC is equal to minus 0.03 by 10, and theta CB is the same. For theta B equal to 1, theta AB is equal to 0. Theta BA from the chord to the tangent is 1. From the chord to the tangent is 1, and theta CB is equal to 0. Here theta AB is equal to 0, theta BA is equal to 0, theta BC is equal to 0, and theta CB is equal to 1. So note one thing is that when you only have a rotation, okay, the new definition of theta and the old definition of theta remain the same. The only difference is when you have a displacement, the theta AB and theta BA, the new definitions are different from the old one. And note that here I do not have any delta, anywhere delta. So once we have that, I can write down theta AB as equal to 0 theta B, so 0 times theta B plus 0 times theta C plus 0.03 upon 10 theta BA is equal to 1 times theta B, 0 times theta C plus 0 and theta BC is equal to 1 into theta B plus 0 into theta c minus 0.03 by 10, and theta cb is equal to 0 times theta b plus 1 times theta c minus 0.03 upon 10. So, these are my equations, and now I substitute these into my slope deflection equations. And what do my slope deflection equations look like? M AB is equal to 4 EI upon L theta AB plus 2 EI upon L theta BA plus fixed end moment AB. Note that in this particular case, since there are no loads, fixed end moment AB is equal to fixed end moment of BA is equal to fixed end moment of BC is equal to fixed end moment of CB, and all of them are equal to 0. Okay. So, I am going to substitute these things in. So, I am going to get 4 EI upon 10, theta AB is 0.03 by 10 plus 2 EI by L, theta B is theta B plus 0.03 by 10 plus 0. So, if you look at it, it's going to be equal to 0.12 plus 2, so 0.16. This is going to be 0.18 EI upon 100 plus 2 EI upon 10 theta B. Okay. Similarly, if you substitute everything in, you will get 0.18 EI upon 100 plus 4 EI upon 10 theta B and MBC is going to be equal to 4 EI upon 10 theta B plus 2 EI upon 10 theta C minus 0.18 EI upon 100, and MCB is going to be equal to 2 EI upon 10 theta B plus 4 EI upon 10 theta C minus 1.8 into 100. Okay. So, these are going to be the equations. And what is, so now again going into the fact that equilibrium equations give us, I am not going in, I have already done this problem earlier. So, I am just substituting them in. Okay. So, I get this one gives me 8 EI by 10 theta B plus 2 EI upon 10 theta C is equal to 0, and the other equation is MCB is equal to 0, and that gives me 2 EI by 10 theta B plus 4 EI by 10 theta C is equal to 0.18. EI is 200 into, I am doing it in kilonewtons, so it is going to be 200 into 6 into 2 into 10 to the power of minus 3 upon 100. And after that, you are going to see that once you substitute these equations, you are going to see that this is going to land up being equal to, when I substitute these equations, you will see that these equations look identical to what I have obtained earlier, and you will see that theta B is equal to minus 514 upon EI, theta C is equal to 2057 upon EI, radians, and when you substitute, you will get exactly the same equations. Okay, so the most important thing is that once I have utilized this procedure, the solution process remains identical. I have just proved that to you with one problem. Okay. Now, what is the advantage of this definition? I will shortly come to that by actually taking up the other problem that I had discussed last time, and that was the frame problem that we had discussed. So, let me just re-put that problem, and I will introduce you to the concept of, see, remember I said that when you were using, what virtual work method did we use for the force method? We use the method of virtual force. Okay, and I had said that I was going to use the method of virtual displacement when I came to using the displacement method. Okay, and that's what I am going to illustrate to you, and this is where it will become obvious as to why I was using this new definition that I had today. Okay, essentially because this is 12 and this is 5. Okay, I am just restating the problem that we had done last time. Okay, today what I am going to introduce to you is the concept of the principle of virtual displacement, and we will see how last time, if you remember, that to be able to generate the third equation, we had to go through quite a bit of involved computation of where we computed shears, etc. Once I give you slightly more complicated problems, especially with inclined members, you will see that this is going to become a very, very messy affair, because not only will you have to compute shears, you will have to compute axial forces and then resolve them, find out the vertical reactions, horizontal reactions, all kinds of things, just to be able to get the third equation. Okay, you will probably have to solve 10 different equations to ultimately get to the third equation. It gets quite messy. Okay, and I will illustrate this concept to you as we go along. There are several lectures that I am going to spend on actually solving example problems for you. Okay, so but I will introduce the concept in today's lecture so that the concept remains clear in our mind while we are solving all the particular problems, and I am going to introduce the concept using this example problem which we have already solved in the last lecture. Okay, so just wanted to put the thing down and then go back to the concept that we are going to have. Remember that I am not going to go through the steps of trying to define what everything is. I am just going to put down my new definition. These are my degrees of freedom, theta b, theta c, and the translation of this delta. Okay, then I have this load here. Here I have a load of 50 kilonewtons and I have a moment of 250 kilonewton meter. I have 100 kilonewton load here and 20 kilonewton load here. Okay, this is 20 meters and this is 15 meters. Okay, so these are the degrees of freedom, theta c, theta b, and delta. One thing you must note, that always my structure degrees of freedom are implicitly assuming this as my structural z coming out. So you will see that if I have a displacement in this direction, it is taken positive in this direction. A rotation is taken positive in this direction so that it comes out of the paper, which is in the positive z direction. If I ever have any displacement in the y direction, I will have it positive in the. So, my definition always is very, very it is completely related to the idea of a positive displacements are along the positive axis of the structure. So, that is why you will see, that is the reason why I always define anticlockwise moment as positive, because that then gives me the concept of positive. It can be generated very easily, because positive degree of displacement corresponding to degree of freedom is aligned along the directions. Okay. Now, let us look at this. First and foremost, we have to compute the fixed end moments, and there is no problem in computing the fixed end moments. The fixed end moments are identical to what we had in the last time, and if you look at it, you will see that the fixed end moment, let me just go through and quickly get you the fixed end moments. Here, this is A, this is B, this is C, this is D, and if you look at fixed end moment at AB, it is equal to plus 22.2. Fixed end moment at BA was equal to minus 44.4. Fixed end moment at BC was equal to plus 288 kilonewton meter, and fixed end moment at CB was equal to minus 192 kilonewton meter. Okay. So, this in the computation of the fixed end moments, you do not have any specific problem. Okay. So, fixed end moment, there is no problem. Now, the only thing is that we need to actually go and define the displacements corresponding to the degrees of freedom and find out how the structure moves. So, now I have theta BA equal to 1. So, theta BA equal to 1 is going to give me this, and that is it. This is 1, this is 1, this is theta B equal to 1, and theta B equal to 1 automatically assumes that theta AC is equal to Z and delta is equal to C. Then I am going to put theta C is equal to 1, theta C equal to 1 is going to give me so all I have. Remember that for rotations the definitions do not change. Now let us put delta gives me this. This is delta and delta. Okay. So, this is equal to delta equal to 1. Now, you see our definition is from the chord to the tangent. So, if you look at this particular point, what is theta AB equal to here? 0. What is theta BA equal to? 1. Theta BC equal to 1, theta CB 0, theta CD 0, theta DC 0. Here theta AB 0, theta BA 0, theta BC 0, theta CB 1, theta CD 1, theta DC 0. No difference. Remember that whenever you have a rotation, there is absolutely no difference in the computation. I mean, as last time and this time. Now, here once you have a displacement, it all changes, because from the chord, so the chord is the one that connects the displaced positions of from the chord to the tangent, So, what is theta AB equal to? See, delta by 15. So this angle, if you look at it, is delta by 15. So theta BA, now look at it, from the chord to the tangent anti-clockwise. So it's positive 415. What about theta BA? Similarly, from the chord to the tangent anti-clockwise 4 by 15. What about theta BC? From the chord to the tangent 0. From the chord to the tangent, theta CB is equal to 0. And from the chord to the tangent, anti-clockwise, positive, theta CD is equal to 4 by 15. Sorry, not 4 by 15. Delta by 15. So this is delta by 15. And DC delta by 15. Okay, so we have figured out everything in terms of the displacements. Okay, and therefore I can write down theta AB is equal to 0 into theta B plus 0 into theta C plus delta by 15. So this is just delta by 15. Theta BA is equal to 1 times theta B plus 0 times theta C plus delta by 15. Theta BC is equal to 1 into theta B plus 0 into theta C plus 0 into delta. Theta CB is equal to 0 into theta B plus 1 into theta C plus 0 into delta. Theta CD is equal to 0 into theta B plus 1 into theta C plus delta by 15. Theta DC is equal to 0 theta B plus 0 theta C upon delta by 15. So these are my rotations, right? These are my rotations. So now all I need to do is find out the moments, and so M AB is equal to I'm just putting them down. I'm not going to actually calculate. I mean, by now, just by substituting into the equations, you will get plus 6 EI. You just plug this in, you will get 6 EI delta. Okay, 4 EI by L 15 theta B plus 6 EI by 15 squared delta. When you plug this in and you put, you will get 4 EI into theta plus 2 EI blah blah blah, and you will get all this. This is exactly what you will get. Okay, this is by substituting these two into the equations for this thing, and then you have the fixed end moment. So this is going to be equal to plus 22.2, and this is going to be minus 44.4. This way, by substituting BC and CB, you can find out MBC and MCB, and you can find out MCD and MDC. Okay, just by substituting them in. I'm not writing those down. Let me just put forward the thought process to you. Okay, so I've got my, essentially I know now MAB as a function of theta B, theta C delta, all of them. MBA. Of course, it's not necessary that all of them will be a function. For example, MAB does not have theta C in it. Okay, but I'm just putting down in general that these will be functions of this, MCB function of some other function, sorry, F1, F2, F3, F4, okay, and mcd is going to be equal to f5 of theta b, theta c and delta, and mdc is going to be f6 theta b, theta c. All different functions, but essentially functions, and then there are the fixed end moments. Okay, so essentially these are my real moments, and these happen due to what? Due to the loading that we have on the structure. Okay. So now I am going to use the principle of virtual displacement. What am I going to do? I am going to say that I am going to apply 3 different independent virtual displacement patterns. So, what are my 3 independent virtual displacement patterns? One is this, one is this, one is this, and I will find out these are the virtual. Now, note that these are now virtual displacement patterns, and I am going to find out the work done by all the forces, okay, subjected to these virtual displacements. So, the work done by the real forces subjected to these virtual displacements is going to give me the work done, the virtual work done in the structure. Okay? And once I have the virtual work done in the structure, I can do what? I can then write virtual work done by the external loads equal to the virtual work done by the internal loads, and once I put that equal, or the total virtual work is equal to 0, and from that I get an equation. Note that what will be the equation in terms of? The equation will be in terms of theta b, theta c, because these are the internal forces, and I am going to find out for each displacement pattern what are the the thetas, and once I have those thetas, I can just say that what is the work done by the internal forces. Look at it. If this is my virtual displacement times, so it is going to be theta AB into MAB plus theta BA into MBA, etc., etc. In that way we can continue doing. So that is my equation, virtual work equation, and that virtual work equation is what is going to give me the 3. And since I have 3 independent, I will get 3 independent equations. If I get 3 independent equations, I can solve for the displacements. I have 3 equations, 3 unknowns, I can solve for them. Okay. So, that is in essence the method of virtual displacement, and now what I am going to do is I am actually going to put it into practice. Okay. Actually take this particular problem. So, let me just put them down what these are, and you will see that this is equal to, I am putting it down, 2 EI by 15 theta b plus 6 EI upon 15 squared delta plus 22 this is equal to 4 EI by 15 theta b plus 6 EI upon 15 squared delta minus 44 by 4. This is equal to 16 EI by 20 theta b plus 8 EI upon 20 theta c plus 288. This is equal to 8 EI upon 20 theta c plus 16 EI upon 20 theta b, this is theta c, minus 192. This is equal to 4 EI upon 15 theta c plus 6 EI by 15 squared delta, and this is equal to 2 EI by L 15 c plus 6 EI upon 15 squared delta. Okay. These are the moments which you can get, and then what is the next step? The next step is to find out the work done by all the forces. So, note that what we have over here is, let us look at what happens. Okay, what you have here is I'm breaking it up because I need to know what is the work done by all the forces. Okay, so here you will have M A B, here you will have M B A, okay, here you will have M B C, here you will have M C B, here you have the load 50 and a moment 250. Okay, then you have the moment MCD, and then you have the moment MDC. Okay, these are all the moments, and note that I'm just putting down all the loads. This is 100 and here you have 20. Okay, so these are all the things. Now one aspect that is very important is that when you have loads acting on the member, what you need to do is you need to find out the reactions at this. Think of this as a simply supported beam with MAB and MBA. Okay, what I need to compute is, for getting the virtual work properly, I need to find out the reactions at the end of the member due to this. So since I'm considering it to be simply supported beam, the reactions are going to be equal to what? This is 5, this is 10. So if I find out the reaction, I'm only finding out the reaction due to the load only. Remember that. Only the load, not due to the unbalanced moments, etc. Only the load. So if I look at it, what is the reaction at this point due to this load? Okay, if I take moments, it's going to take moment about that point. You're going to have 5 into 20. Okay, so this is going to be anti-clockwise, and if I put this in this direction, it's going to be clockwise. So this into 15 is equal to 20 into 5. Okay, and if you look at this, so this is going to be equal to 100 upon 15, and this, if you look at it, is going to be 200 upon 15. Similarly, here we're going to have 8 and 12. So just due to the load alone, you will see that this is going to be equal to 1200. So this is going to be 60 and this is going to be 40. Of course, if I substitute, this is going to be 20 by 3 and this is going to be 40 by 3. Okay, so what have I done? And since on this member there is nothing, note that these are applied at the nodes, so I don't need to find out. It's only the member I need to find out the reactions. Okay, so now, so I've just found out the reaction. So now what is my virtual work equation? I'm going to put theta b equal to 1. Okay, so theta b, theta b. So this is my virtual displacement pattern. So theta b into the moment at b, which is 0. Okay, this is the external work done. I'm calculating all the external. Note that these I have translated, so these are no longer, member loads are never external. It's only joint loads which are external. So this joint, how much does this joint displace by under theta b? If we look at it, let me look back at the equation that I have drawn. So see, this is my theta b. This is for, now I'm giving this a virtual displacement. So virtual displacement, okay, I'm going to have that this into 1, nothing, 0. This is not going up, neither it's rotating. So these two don't do any work. Okay, so the external virtual work is equal to this. And what is the internal virtual work? Internal virtual work, if you look at it, the MBA does work. So it's going to be MBA into theta b, because it's 1 into theta b. Okay, and note that the moment is this way, the rotation is this way, so it's positive work. Then plus what else? You will have m b c into theta b. Okay, and then let's look at all the work done by this and this. These don't undergo any displacements. Okay, neither do those and neither does that. So this is my equation. Okay, so this is my equation. This is the external virtual work, this is the internal virtual work. So if I look at this, this is going to give me equal to MBA plus MBC into theta b is equal to 0. Now this is true for any arbitrary theta b. So this implies that MBA plus MBC is equal to 0. Note that this is exactly the equation that we get when we put equilibrium conditions in the previous case. The only thing that we did was we computed the work, virtual work done. So virtual work, remember I had said that the method of virtual displacement essentially replaces the equilibrium conditions, and I am showing this here, that I am getting the same equilibrium conditions that I get. Now let me put theta c, and I have the same equations. Let me put the arbitrary equation that theta c is equal to 1. So then the work done will be theta c, that's the arbitrary, and what is the this thing? Theta c is in this direction. So what is the moment at that point? You will see that it's clockwise moment, so you're going to get 250 into theta c. This is the external virtual work. All the other external forces, including the support reaction in the joint, do not undergo any displacements. So this is going to, all of them are going to be 0, and so the internal virtual work is going to be MAB into theta AB, which is 0. You know, theta AB in terms of delta, this theta is 0. So it's going to be all MBA, theta B 0, etc. You will see that the only terms that exist will be MCB into theta C plus MCD into theta C. Okay, and none of the other people do any work, and so this one, if you look at it, is going to be MCB plus MCD plus 250 into theta c is equal to 0. Now this has to be true for all arbitrary theta cb, so I get equal to 0. Now these look like equilibrium equations, but they are not. They are actually weak solutions. They are actually the work done by this. Okay, so I have shown to you that essentially the equations, when I put theta b equal to 1 and theta c equal to 1 as the virtual displacement patterns, I get back my MBA plus MBC equal to 0, which was the simple equation that we had got earlier, and I also got that MCB plus MCD plus 250 is equal to 0. In other words, when I put the theta b and theta c virtual displacements, I essentially get back the simple equations that I had developed by taking equilibrium of the joints of joint B and joint C in the earlier case. Okay, now I'm going to stop over here because I've come to the end of my lecture. In the next lecture, I'm going to show to you that by taking the virtual displacement delta equal to 1, how I can generate a third equilibrium equation easily without having to go through a whole host of equilibrium conditions for each individual member. Okay, so on to the next lecture, where I'll show you the actual power of applying the method of virtual displacement. Thank you.